Welcome students. Today I will be taking up the second topic of electrochemistry, that is the galvanic cells or voltaic cells it is also called, and how to apply the Nernst equation in galvanic cells. This is very important topic. We can expect one compulsory question from this area. We can expect, because if you see the previous year's questions, many questions came from this area. First we will briefly see a few points so that we can easily understand the questions. See, when we see the notation, when they give notation of the galvanic cell, left side generally solid electrode, then aqueous solution will be there, and aqueous solution and solid electrode. This is how they will represent. Now, left side of this double slash represents salt bridge, left side of this is the anode information, right side of this is the cathode information, because electrons travel from anode towards the cathode. That's why this is the way we will represent. Now, EMF of the cell. How to calculate EMF of a galvanic cell? Reduction potential of cathode side. Cathode side means right side of the salt bridge. So, right side related reduction potential value minus anode related reduction potential value. Cathode reduction potential minus anode reduction potential. This will give you the EMF of the cell. Next, suppose if E cell, EMF of the cell is positive, then we can say reaction is feasible, means spontaneous, means that will take place. Suppose if it is negative, we can understand the reaction won't take place at all. Suppose if EMF of cell is 0, it indicates reaction is at equilibrium state. Next, this is called the Nernst equation, which is very important. EMF of the cell is equal to E naught of cell, means EMF of the cell at the standard conditions, minus 0.0591 minus 0.0591 by N. N means number of moles of electrons involved in the galvanic cell functioning into logarithm of Q. Here log base 10, not base E, log base 10, and Q is the reaction quotient. That means when you write a balanced equation, products by reactants raised to their stoichiometric coefficients, that is called the reaction quotient. We will see some examples so that you will understand easily. This is called the Nernst equation at 25 degrees centigrade. Because when you take temperature as 298 Kelvin, then only you will get this value 0.0591. If they don't mention anything about the temperature in the question, understand by default it is 25 only. Next, E naught of cell is equal to 0.0591 by N into logarithm of equilibrium constant. Sometimes they will ask you to find the equilibrium constant of a redox reaction or galvanic cell reaction. Then how to calculate? Using the E naught of cell in this formula, you can get the equilibrium constant. Next, delta G means Gibbs free energy. Delta G is equal to minus NF EMF of the cell, where F is called what? F is the 96,500. 96,500 coulombs is called 1 Faraday, means charge of 1 mole of electrons. That is what F here, which is 96500 coulombs into EMF of the cell. That's what written here. N is moles of electrons involved in that galvanic cell reaction. F is the 96500 coulombs. One important point I need to mention here. See, in Faraday's laws also you will see the N. That is the N factor. In galvanic cell or Nernst equation also you see N. But remember, this is not the N factor. This is the total number of moles of electrons involved in a galvanic cell reaction. Means electrons involved, total electrons involved at cathode, or total electrons involved at anode. That is the N here, because at a cathode or anode, number of moles of electrons involved will be always same only, because same electrons transfer from anode side towards cathode side. That's why the value will be same, and that is not the N factor. N factor is definition wise. N factor is what? Number of moles of electrons involved per mole of species. That is the definition of N factor, which we need in the Faraday's laws application. Don't get confused with these two. Next, see, write cell equation for the cell. For these from these two examples, let's see how to write the cell equation. See, this is the notation of the galvanic cell. Sn/Sn plus 2. This is the anode information. This is the cathode. See, remember one point using which you can easily write the cell equation. This shortcut, keep it in mind. See, just follow the left to right direction you follow to write the balanced equation. In most of the cases it will work. One important case where it will fail, I will mention. Okay, apart from that, in all other cases, just apply this shortcut. Just follow the equation from left to right in the cell notation, whatever is given. Means tin gives Sn plus 2 and Pb plus 2 gives Pb. Pb plus 2 gives Pb. That's it. Now after that, see the whether it is balanced or not. If it is not balanced, balance the equation and then proceed. I mean, here in this question, just we need to write the balanced equation. We need not calculate any EMF of the cell, nothing here. So just write the balanced equation and stop here. And if you see the number of electrons involved for lead also 2, tin also 2. So if number of electrons are balanced, atoms are also balanced, that is called the balanced chemical equation. It is already. Next, look at this. Next, in the next electrode, in the next galvanic cell notation, left side is the hydrogen electrode, right side is the chlorine, halogen electrode is there. Now here, if you notice here, there is no double slash here, which means there is no salt bridge. Sometimes we will get a doubt whether a salt bridge is necessary, compulsory in a galvanic cell or not. It is not compulsory. Suppose if electrolyte is common for both the half cells, cathodic and anodic half cells, then salt bridge is not necessary because both electrodes now will be in the same electrolyte and there is no need of the salt bridge. Suppose if cathode rod is dipped in some different electrolyte and anode rod is dipped in a different electrolyte, then there will be a salt bridge necessary to connect these two half cells. Okay. So since there is no double slash, in place of that there is a HCl in between these two slashes. We can understand from this the common electrolyte is HCl and there is no salt bridge here. Okay. Now how to write the balanced chemical equation? Here also follow left to right, but remember one thing here. In case of halogens, right to left. In case of others, metals or hydrogen electrode, just follow the left to right sequence to write the balanced equation. So see here in the first case only metals are there. So left to right I have followed. Here hydrogen H2 gives H plus I am writing, and since it is a halogen, what you do, opposite direction you come. Cl2 gives Cl minus. Remember this important difference. Now if you remember for halogens we will follow right to left, then you can easily apply this shortcut everywhere. Now so H2 gives H plus, and what is the other one? Cl2 gives Cl minus. Cl2 gives Cl minus. That's it. And after that, now take care of the balancing. First balance the atoms. 2 hydrogens, so I'll put 2 here. 2 chlorines, 2. So if you look at the hydrogen also, electrons involved is 2. Halogen also 2 electrons. It is the balanced equation. So this is how you have to write the balanced equation. And remember, whenever you are applying the next equation, you must balance the equation like this first. Without balancing, never apply the next equation. Let's see the next question. Find E naught of cell. There is a data given, E naught of zinc and copper, and cell notation is also given, this galvanic cell notation, and we need to find the E naught of cell. Now see here, Zn plus 2 to Zn. The meaning of this notation is, first Zn plus 2 is there, then Zn is there, meaning Zn plus 2 to Zn means reduction. Decrease in oxidation state means reduction. So reduction potential value of zinc is given. Similarly, reduction potential value of copper is given. This is the data given. Reduction potential value of zinc and copper. Sometimes students get confused. Sir, for both cases they have given their reduction values only. That means they are saying copper is also reducing, zinc is also reducing. That's what the meaning of the question. No, don't decide from the data. This is the given data. Wherever it is helpful, use that data. But don't judge the scenario, actual scenario using this given data. These are the reduction potentials. They are not saying zinc is undergoing reduction, copper is undergoing reduction. Then how do we know which is undergoing reduction and oxidation? Look at the galvanic cell notation. Left side of the salt bridge. Now salt bridge means double slash. Left side is the anode, right side is the cathode. Means zinc is the anode, copper is the cathode. That is how we have to decide. Don't decide from the E naught values. So this is the anode, this is the cathode. We know that E naught of cell formula is what? Reduction potential of cathode minus reduction potential of anode. So cathode is copper, so its reduction potential value is 0.34. Substitute. Anode is zinc and its value is minus 0.76. Be careful there. And minus of minus is plus, overall is 1.1. Next, remember this point. reduction potential, if reduction potential value is more, then reducing strength or reducing power of the species will be less, opposite. Reduction potential more, reducing power will be less, opposite, inverse. And what is this reducing power? Remember, reducing power means not ability to get reduced. Reducing power means ability or power to reduce the other one. That means if it is reducing the other one, this is undergoing the oxidation. Similarly, oxidizing power. Oxidizing power means oxidizing the other species. If reduction potential is more, it will easily undergo the reduction. Therefore, it easily oxidizes the other one involved. So, remember these points. Now, look at the question. E naught A plus 2 to A is given. Similarly, B reduction potential given. If you see, these are all reduction potentials only, because plus 2 to 0 means reduction. Similarly, oxidation state plus 2 to 0 means reduction. Reduction potentials are given, which has the highest reducing power. Highest reducing power means we have to look at the lowest reduction potential value. Which has the lowest, including the sign you have to see. Which is the lowest? Minus 3.1. So, B has the highest reducing power. But now see, if you look at this here, there are two options involving B. One is B plus 2. If you see, other one is B. Now, which one we have to select? Be careful here. Now, what we are saying, highest reducing power. Highest reducing power means it is supposed to reduce the other one. In the process, it will undergo the oxidation. Now, B undergoes oxidation or B plus 2. Look here. B can undergo the oxidation and convert into B plus 2. B plus 2 can undergo only reduction. So, therefore, highest reducing power means the species should reduce the other one, and hence it undergoes oxidation from B to B plus 2. Therefore, B is the species with highest reducing power. So, be careful in such problems. Next, let's see this question. SRP. SRP means standard reduction potential of three metals. A, B, C are given. Which metal can displace the other metal from its aqueous solution? See, in the reactivity series, in reactivity series of metals, actually that reactivity series is arranged keeping in view of reduction potentials only. From lithium to gold, if you see the reactivity series, lithium is the highly reactive. As you go down, copper, mercury, etc., gold you will get. Now, gold is the less reactive in that series. Now, on what basis they have arranged this? On the basis of the reduction potential. Top to bottom reduction potential increases. Okay. So, we already know that if upper metal is there, upper metal can displace the lower metal from its salt. We know this already. So, which metal can displace other metal from its aqueous solution means the metal which is above in the reactivity series means the metal which has less reduction potential can displace the metal which has the more reduction potential. Suppose, look here, first let's arrange these three metals in the increasing order of reactivity series. Top to bottom, E naught Rp increases in case of reactivity series. So, let's arrange in this manner. So, which one is the lowest here? Minus 2 is the lowest. That means B is the lowest. Then comes what? 0.4. Then comes C. So, B lowest, C is the highest. That means B can displace ions of or aqueous solutions of the A and C salts. A can displace aqueous solution of C salt. So, A displace B and C. That is wrong. B displace A and C. Yes, B displace because B is upper. It can displace the A and C from its aqueous solution. This is right. C displace A and B. No, that is quite wrong. B displace only A. Not correct. B displace A as well as C also. This is how you have to decide. Identify correct statements. Zinc rod can be used to stir CuSO4 solution. Suppose if I take the CuSO4 solution, copper is in +2 state, and if I use the zinc rod to stir the solution, then what happens? If reaction does not take place between them, fine, we can use that rod. But if reaction is taking place, then we should not use that rod to stir something. Then it will dissolve in that. The whole purpose of stirring is lost. Now, how to decide whether the reaction takes place or not? We know that zinc is above in the reactivity series, copper is below. Therefore, zinc can displace the copper from its salt. Zinc means upper metal, displace the lower metal from its salt solution, and reaction takes place like this. Therefore, we cannot use the zinc rod to stir the CuSO4. This is wrong. In Daniell cell, current flows from copper side to zinc side. Now see, Daniell cell. In Daniell cell, very important galvanic cell it is. Zinc side is the anode, copper side is the cathode. So, if zinc side is anode, copper side is cathode, always electrons flow from anode side to cathode side. This is the direction of electrons. But what they are saying, Daniell cell current flows from copper side to zinc side. Electrons flow from anode, zinc side to cathode, copper side. Whereas current is the direction of current is opposite to that of direction of electrons. So, direction of current is like this. Cathode to means copper side to zinc side. That is only they are saying copper side to zinc side. Therefore, this is the correct statement. Cations move towards copper electrode in Daniell cell. Now see, in the Daniell cell, what is happening? Cathode side copper is involved. Involved in what? Cathode side always reduction takes place. Means suppose if this is cathodic half cell, this is the copper rod, Cu plus 2 go here and take the electrons from here and undergo the reduction. So, copper cations move towards the electrode, take the electrons and undergo the reduction. That's what happens at the cathode side. So, this statement is saying what? Cations move towards copper electrode in Daniell cell. Yes, Cu plus 2 ions go there and taking up electrons. So, that is right only. Salt bridge is essential for any galvanic cell. No. In the previous slides only I mentioned, salt bridge is not essential. Suppose if two different electrolytes you are using in two half cells, yes, it is essential. If common electrolyte is involved, no, salt bridge is not required. Therefore, essential is wrong here. Next. Now see, there is a reaction given. Fe plus 2 gives Fe plus 3, cerium plus 4 gives plus 3. And there is a data also given. Fe plus 3 slash Fe plus 2 means reduction potential of Fe plus 3 is given as 0.77. And cerium plus 4, this is also reduction potential. Both reduction potential data is given. But what is actually undergoing reduction? Cerium is undergoing reduction, whereas iron is undergoing oxidation. So, from the equation you have to decide, not from the given data. Given data is both reduction potentials only given. And K equilibrium. K of the equation means what? Equilibrium constant of the equation is approximately how much? Now see, we know what is the equilibrium constant. How to get E naught of the cell? We know in the beginning slides only we have seen the formula connecting the E naught of the cell and the equilibrium constant. By using that we can get the equilibrium constant. Now see, first let's calculate E naught of cell, using which we will get the equilibrium constant. E naught of cell is E naught reduction potential of cathode minus E naught reduction potential of anode. So, where reduction is taking place, that is cathode. Wherever oxidation is taking place, that electrode is anode. So, cerium is the cathode, iron is the anode. So, cerium reduction potential minus iron reduction potential, if you take, you will get the E naught cell. So, the values which are given in the question substitute here, you will get 0.84. So, that is the E naught of the cell. Now, we know the formula. E naught of cell is equal to 0.0591, approximately 0.06 you can take, by N into log equilibrium constant. What is N here? If you see the electrons, plus 2 to plus 3, if you take iron plus 2 to plus 3 or cerium plus 4 to plus 3, anyone you can take, you will get the moles of electrons as 1. Don't add these two electrons and say 1 plus 1, 2. That is the N. No. Because electrons involved in reduction side or oxidation side means they will be always equal. Don't add them. That is the N here, which is 1. And equate it to the E naught cell, 0.84. Then you will get equilibrium constant. Log K 14 means what? K is equal, here base is 10 I mentioned. So 10 power 14 is the K value, equilibrium constant. This is a disproportionation reaction. Cu plus is converting into Cu as well as Cu plus 2. Now here, if you see, generally sometimes students think that here N value, number of moles of electrons, they will take 2 and solve the problem. No, look carefully. Out of 2 Cu plus, one is undergoing plus 1 to 0 means what? Reduction. The second Cu plus is undergoing oxidation. One is undergoing reduction, other is undergoing oxidation. Either you take reduction or oxidation, you will get moles of electrons or electrons involved is 1 only. See, Cu plus gives Cu, here also 1 electron. Cu plus gives oxidizing to Cu plus 2 case also 1 electron. So N is 1 here and E naught cell is equal 0.06 by N into log K. Substitute E naught cell, which is given in the question, 0.36, and this is E naught cell, and therefore there here 6 times it will cancel, and log base 10 is there. So for K is equal 10 power 6 you will get. This is the galvanic cell. Anode side nickel is there here, cathode side chlorine is there, and this is the molarity of nickel ion. This is the molarity of the chlorine ion. Standard reduction potentials of nickel is given, chlorine is also given. This is nickel reduction potential, this is chlorine reduction potential. Find EMF of the cell. Now see, whenever you see the concentrations here, like this they have given the concentrations, apart from the 1 molarity, understand that you must apply the next equation. So next equation, E is equal to E naught cell. Approximately I am taking 0.06 here, N log Q. Now what is Q here? See, to find this Q, first you need to write the balanced equation, then only you will get what is that Q. Now what is that balanced equation? See, here nickel gives Na plus 2, because I already mentioned in the beginning only. For halogens, follow right to left. For metals, hydrogen, follow left to right. So nickel is a metal, follow left to right, nickel gives Na plus 2. For halogens, be careful here, you have to write Cl2 gives Cl minus. So Na gives Na plus 2, Cl2 gives Cl minus. Since there are 2 chlorines, balance it with 2. So this is the balanced equation. Now here if you take nickel or chlorine, whatever as you like, whatever you take, you will get the same electrons only, which is 2. Therefore, number of electrons is 2, because if you take nickel or chlorine, you will get 2 electrons only. For 1 chlorine, 1 electron. Since 2 chlorines, 2 electrons. Next, reaction quotient. Reaction quotient is important for next equation to apply. Reaction quotient is products Na plus 2 power 1, Cl minus power 2, Cl minus concentration power 2 divided by reactants. Reactant solid nickel we don't take, and chlorine, which is a gas, therefore for gases we have to take the pressure. Since in the question they have not given information about chlorine gas pressure, assumed it to be 1 atm. So 1 atm here, substitute the concentration of nickel and chlorine, you will get the Q value. Then E naught cell is equal, because in next equation we need E naught cell also. So E naught cell is equal to reduction potential of cathode, which is cathode chlorine, right side one, minus reduction potential of anode. By substituting the given data from the question, you will get the E naught cell. So whenever you have to calculate the EMF of the cell, that means for a given concentrations, EMF of the cell to calculate, you need to apply the next equation. To apply that equation, 3 things you need: E naught cell, N, and the reaction quotient. So N, reaction quotient, E naught cell we have calculated. Now substitute those values in the next equation. E naught cell minus 0.06 by n logarithm of q. So by substituting these three, we will get the EMF of the cell as 1.79. Find delta G naught is given and find E naught of cell. See, delta G naught is minus NF. In the beginning we have seen this formula in the beginning slides. Now see, N is the moles of electrons involved, F is 96500 coulombs, E naught cell. E naught cell is also given in the question. The whole question now depends upon the N value. If you calculate or find it out properly, you will get the correct answer. Otherwise, everything goes wrong. Now, how to find N? See here, aluminium is going from 0 state to +3 state. Oxygen is going from 0 state to -2 state. Oxygen is getting reduced, aluminium is getting oxidized. Either you take aluminium or oxygen, anyone you take, you will get the same answer only. N value. Let's take the aluminium. 4 by 3 aluminiums involved in overall. See 4 by 3 here. Here also 2 by 3 into 2 is 4 by 3. 4 by 3 aluminiums involved. For each aluminium, what is the change in oxidation state? 0 to +3. Change is 3. That means 3 electrons are involved. Since there are 4 by 3 aluminiums, for each aluminium 3 electrons are involved. So total moles of electrons involved is 4. Total moles of electrons involved is 4. If you take oxygen also, you will get the same only. 2 oxygens involved, each oxygen 2 electrons. So 2 into 2, 4. So therefore minus 4, N is 4 here. And E naught cell, we need to calculate that only. 827 kilojoules. Don't forget to convert this kilo. If you look at the options, there is a too much deviation or too much difference is there in the options. So instead of calculating exactly, we can approximate and we can save the time. In examination, time is important. So here, what I will do first, I will calculate. First, I will cancel this zeros, 2 zeros, and one more 0 if I bring here, 965 becomes into 96.5 if I bring this 10 cube right side. Now 96.5 means approximately I will take it as 100. So finally what we are getting, minus 827, minus also get cancels in fact, minus 4 into 100 into E naught cell. Now 827, you can take it as approximately 800 so that 4 will cancel easily. So if you take 800 here, then 4 into 200 is 800. So 200. So finally approximately you are getting E naught cell as 2. So whichever option has close value to 2, that is the right answer. So that means see here, it is close to 2.14, close to 2 value. So this is the right one. So in examination time, saving time is more important. So don't go for exact calculation. First look at the options. If there is a large variation is there, then go for the approximation. Okay, look at this question. Here both sides hydrogen electrode only given. Left side anode also hydrogen electrode, right side also hydrogen electrode. Now here H2 gas pressure is 1 atm, H plus is 10 power minus 6 molarity. Cathode side H plus is 10 power minus 4 molarity and H2 also 1 atm. We need to find the EMF of the cell. So whenever concentrations are given beyond besides the apart from the 1 molarity value, then always you must apply next equation to find EMF of the cell. So here concentrations are given, some concentrations are given, so we must apply the next equation. Before applying next equation, remember always write the balanced chemical equation. From that only we will get the number of moles of electrons N and reaction quotient Q. So don't forget that. So I am writing the equation. So first here see, since both cathode and anode is the same electrode, hydrogen electrode, to avoid confusion, I will put A for anode, C for cathode. Now see here, H2 is converting into H plus converting into H2. I will put the notation A for anode, C for cathode. So see, H2 anode converting into H plus anode, H plus at anode, H plus cathode converting into H2 at cathode. Whether cathode side or anode side, H2 is 1 atm is only given, there is no problem in that. But anode side H plus is 10 power minus 6. So anode side means this one, which is 10 power minus 6. Cathode side is given as 10 power minus 4. That is the cathode side. Now, now Q value. If Q value we can easily get H plus square into pressure of H2 by H plus square into pressure of H2. That is the Q. And number of moles of electrons, N, as you see clearly 2 moles of electrons involved, N. And E naught cell will be 0 because if left side anode side and cathode side, if same electrode is involved, then reduction potential of cathode minus anode will be always 0. So E naught cell will be 0 for this. So E cell is equal minus 0.06 by N, that means moles of electrons, which is 2, logarithm of H plus at anodes power 2 divided by H plus at cathode power 2. So 10 power minus 6 square by 10 power minus 4 square. Products by reactants power raised to the powers of stoichiometric coefficients. That is how we write the reaction quotient. Then if you simplify, you will get this is 0.03. So minus 0.03 into log 10 power minus 4. So we can bring this minus 4 to the front. So minus 4 into minus 0.03 is 0.12. Log 10 base 10 is 1. So answer is 0.12 volts. Now see, E naught Fe plus 2 Fe data is given. Fe plus 3. Reduction potentials are given. Plus 2 to Fe. Plus 3 to Fe reduction potential value is also given. What they are asking, plus 3 to plus 2 is asking. Fe plus 3 to Fe plus 2 reduction potential they are asking. So remember, when you are dealing with the complete galvanic cell, which involves oxidation and reduction both, then E naught of the cell is just reduction potential of cathode minus reduction potential of anode, simple. But if we are calculating E naught of half cell, this is half cell, which involves some electrons, then follow this method. First see, arrange all species in decreasing order of oxidation states. Fe plus 3, what is the given data, see here, Fe plus 3, plus 2 and neutral Fe. These 3 species are there. Arrange them in the decreasing order of oxidation states. This is now plus 3 to plus 2. Fe plus 3 to plus 2, we need to calculate the value. So I put the question mark here, E naught question mark. We need to calculate that. And Fe plus 2 to Fe. Fe plus 2 to Fe data is given as minus 0.44. So right here. And Fe plus 3 to Fe given in the question as minus 0.036. So this data is given, this data is given. This reduction potential value they are asking. So 2 reduction potentials they have given, third one they are asking, reduction potential. Then follow this method. Now see, here if you see this path plus this path, 1 plus 2 is equal to, you see clearly 3. So 1 plus 2 is equal to 3. So what you do, so in the first path E naught, let's call it, we need to calculate that. Second path, what is the E naught? Minus 0.44 is equal to, third path, what is the E naught? Minus 0.036. First you write like this, but that is not the end. Okay. So and what you have to do, you should do one more step to get to the answer. So after writing like this, then multiply with the moles of electrons involved in the each step, corresponding step. For example, first step, what is the electrons involved? Plus 3 to plus 2 means electrons involved is 1 electron. Plus 2 to 0. Plus 2 to 0 means how many electrons involved? 2 electrons. Plus 3 to 0 means in this path how many electrons involved? 3 electrons. Now multiply with the respective electrons. So E naught is the first path. So first path 1 electron. Second path 2 electrons. So multiply. Third path 3 electrons. So multiply this with 3. That's it. After that you just simplify. Take this to the right hand side and calculate the E naught. That is the Fe plus 3 to plus 2 reduction potential value. That's it. I hope you understand. So these are the important concepts in the galvanic cells. If you see here, various models we have discussed. The most important one, Nest equation. In that Nest equation, when we need to apply the Nest equation, how do we understand Nest equation should be applied in a problem? Remember, there should be concentrations given below the ions, 0.01, 0.001, like that they will give some concentrations. From that you understand, okay, we have to apply the Nest equation to get the EMF of the cell. To get the Nest equation, First, always write the balanced chemical equation, which is undergoing reduction, which is undergoing oxidation, and balance both left hand side and right hand side in the equation. Then write the Q, reaction quotient from that balanced equation, and moles of electrons. Using this, you can get the EMF of the cell in the next equation. And remember, N is in the next equation, N is not the N factor, that is the moles of electrons involved, either in oxidation side or reduction side, and don't add them. Okay. I hope you understand all these concepts. Thank you.